Today, we are going to discuss about the electrochemical grinding process. Coming to the introduction of electrochemical grinding process, the conventional grinding produces components with very good surface finish and dimensional accuracy. But such components are also associated with bursts, comparatively large heat-affected zones, and thermal stresses. These defects are not found in electrochemically ground workpiece. It is also called as anode. During electrochemical grinding, the material is removed by mechanical abrasive action by 10% and by electrochemical dissolution 90% of anodic workpiece. So it means that only 10% of the material is removed by mechanical abrasive action and remaining 90% of the material is removed by electrochemical dissolution process. As in any other electrochemical dissolution based process, workpiece should be a electrical conductive material. Here also the workpiece should be a conductive material. The electrolyte is recirculated in electrochemical grinding. Hence, the effective and efficient electrolyte supply and filtration system should be needed. Just like other electrochemical electrical based machining process, this electrochemical grinding process also required the workpiece should be a conductive material and the electrolyte is also recirculated in electrochemical grinding process so that the electrolyte should be effective and efficient supply system and filtration system is also required. The commonly used electrolytes in electrochemical grinding process are sodium chloride and sodium nitrate. So this is the schematic diagram of electrochemical grinding process. It involves like this is the work table on which we are going to fix this workpiece, and this is the grinding wheel, and these are the abrasive plates which are attached to this electrochemical grinding wheel, and this grinding wheel is attached to this grinding spindle and it is rotated by electricity. And this is the storage tank. Here we are going to collect the place this electrolyte, and from which we are going to supply the electrolyte through the pump filter, and then it will be go through this tubing system, and finally it is entered at electrochemical grinding wheel, and in between this tool, this is the grinding wheel is acts as a tool. In between this grinding wheel and this workpiece, we have to maintain a small inter-electrode gap. Through that electrode gap, we have to supply this electrolyte. So this is also the clear-cut information. It gives the clear-cut information about this electrochemical grinding process. See, this is a yellow shaped workpiece. Previously, it is in the rectangular shape, and this is the table on which we are going to fix this workpiece, and we are going to supply the DC power to the both tool and workpiece. The tool is acts as a cathode, means there is a negative terminal connected to the negative terminal, and this workpiece is acts as a cathode and it is connected to the positive terminal. And this is the electrolyte tank from which we are going to supply this electrolyte through pump, motor, filter, and then it is going to pump in between the tool, that is the grinding wheel, and workpiece through this nozzle. And this grinding wheel is having some metallic bonds. It may be made of like a copper, brass, bronze, like that materials. So this is also gives the same information. So in electrical chemical grinding process, there are 3 zones are available. This is the grinding wheel, the electrochemical grinding wheel, and it is connected to the negative terminal and it acts as a cathode. And this is the workpiece. Initially it is in the rectangular shape. Okay, and it is acts as an anode and it is connected to the positive terminal. And this is the rotation of the grinding wheels in electrochemical grinding process. During this electrochemical grinding process, the machining takes place in 3 zones. Machining takes place in between these 2 workpiece and with help of this grinding wheel. Here we have to know about the 3 zones which are lying in this electrochemical grinding process. This is the zone 1 and this is the zone 2 and this is the zone 3, and these are the grinding abrasives. Okay, in between these abrasives. These abrasives are attached to this grinding wheel. In between this grinding wheel and this workpiece, we are going to supply this electrolyte in between these two. So this is the somewhat the what is the machining zone in between this grinding wheel, abrasive grind and workpiece. If it is zoom like this, then it will give the clear cut information about this one. And this is the tool, and it is acts as a anode, and it is connected to the positive terminal. And this is the wheel, and it is acts as a cathode connected to the negative terminal. And this is the abrasive grains which were attached to this grinding wheel. In between this grinding wheel, we are going to supply this electrolyte, and these dotted lines indicate the electrolyte. This is the deep information in between this tool and workpiece. In electrochemical grinding, there is a grinding wheel, and it is acts as a cathode, similar to the conventional grinding wheel, except that the bonding material is electrically conductive material. So in case of the conventional grinding machining process, the grinding wheel will be there. Those grinding wheel is attached to this abrasive grinds. Those abrasive grinds are non-conductive material. But here, what are the abrasive particles are attached to this grinding wheel? Those sharp edges are made of some conductive materials. Electrolyte is supplied through the inter-electrode gap in between this wheel, grinding wheel and the workpiece. The height of the abrasive particles protruding outside the bonding material of the wheel helps in maintaining a constant inter-electrode gap, because the abrasive particles acts as a spacers. See here in between this is the abrasive particles, and the gap which is present in between this workpiece and this wheel, it is acts as a spacer. In between this space, we are going to supply these abrasive particles. The height of the abrasive particles protruding outside the bonding material of the wheel helps in maintaining a constant inter-electrode gap. The two factors are responsible for such a high wheel life. So in any machining process, the wheel life or tool life is very much important. And here also, the grinding wheel life plays a vital role. So the life of the grinding wheel is mainly depends on two on the factors, like only 10% of the contribution by abrasive action towards the total material removal. So as we discussed in previous, in electrochemical grinding process, the 10%, only 10% of the material is removed by mechanical metal removal process, okay, by means of this abrasive particle, and very small length of the arc of the contact. In electrochemical grinding, the area in which the machining takes place can be divided into three zones. That is the zone 1, zone 2, and zone 3, as we showed in the last figure. This is the zone 1, and this is the zone 2, and this one is the zone 3. And we are going to discuss about this what exactly happening in this zone 1, zone 2, and zone 3. In zone 1, the metal removal is purely due to electrochemical dissolution, and it occurs at leading edge of the electrochemical grinding wheel. So in zone 1, the material is completely removed due to the electrochemical dissolution. Means the chemical reaction takes place between this workpiece and the chemical or the electrolyte which we are going to supply in between the grinding wheel and workpiece. The rotation of the electrochemical grinding wheel helps in drawing the electrolyte into the inter-electrode gap. See this diagram. See, while it is rotating like this, it sucks this electrolyte and it enters and it create a path, and otherwise it sucks this chemical electrolyte in between this grinding wheel and the workpiece. As a result of this electrochemical reaction, so whenever this electrolyte or chemical solution is passed in between this tool and the grinding wheel and the workpiece, the electrochemical reaction will be takes place, and because of this reaction, the contaminate electrolyte resulting in a lower conductivity. Because during this machining process, what will happen? Gases will be developed, and because of these gases, the electricity is not transferred that much in between the two grinding wheel and the workpiece, so that the low conductivity will be takes place. In fact, the percentage of sludge to some extent increases the conductivity of the electrolyte. Normally, what will happen? Whatever the material is removed from the workpiece, that acts as a sludge in between lies in between this grinding wheel and workpiece. Because of this, what is it? Sludge. Normally, the electrical conductivity will be increased, but while because of these gases present in it, in between this grinding wheel and the workpiece, the electrical conductivity is reduces. The net result is the decrease in the value of the conductivity of the electrolyte. It yields the lower value of inter-electrode gap. So in machining zone 1, whenever we supply the electrolyte in between this grinding wheel and workpiece, because of the chemical reaction, some gases will be produced, and because of these gases are also acts as a bad conductors of the electricity, and finally it is going to reduce the inter-electrode gap. As a result of this, what will happen? These abrasive particles touch the workpiece surface and starts to removing the material by abrasive action. So whatever the sharp edges of abrasive particles are attached to this grinding wheel, those grinding wheels will touch the surface of the workpiece, and then it removes the small amount of metal from the workpiece by means of the abrasive action. Thus, a small part of the material is removed in form of chip. Further, electrolyte is trapped between these abrasive particles and the workpiece surface, and it forms a tiny electrolytic cell, as shown in the previous figure. See here, this is the tiny electrolytic cell which is formed in between this abrasive particles and these particles. And because of this tiny cell, a small amount of material is removed from the workpiece, electrochemically dissolved. Means in zone 1, most of the material is removed by means of this electrochemical reaction, and very small amount of material is removed by means of the mechanical abrasive action. The electrolyte is being forced into this inter-electrode gap in zone 2 by the rotational motion of the wheels. So after zone 1, the chemical solution or the electrolyte is dragged into the zone 2 because of this movement of this grinding wheel. As a result of this, the local electrolytic pressure increases in this part of zone. It suppresses the formation of gas bubbles. In the zone 1, what we discussed, because of the chemical reaction, some gases will be developed, and because of those gases, the conductivity will be reduced. But in case of the zone 2, because of the pressure, the gas bubbles will be reduced, so that it suppresses the formation of the gas bubbles, and finally it is going to increase or yielding the higher MRR, means metal. It increases the metal removal rate. The chemical or electrochemical reaction may result in the formation of the passive layer on the workpiece surface. So here the one passive layer will be formed on the workpiece surface. So in this zone 2, abrasive grains remove the material from the work surface in the form of chips, and also remove non-reactive oxide layer. So whatever the passive layer is formed during this zone 2, that is also removed by means of this abrasive grains. The most of the metal oxides forms are insoluble in water and electrically non-conductive. The removal of non-reactive oxide layer promotes the electrolytic dissolution. It exposes the fresh metal for further electrolytic action. Hence, it is also called as a mechanical assisted electrochemical grinding process. So whatever the passive layer is formed, those passive layer is removed by means of this mechanical reaction. That's why it is mechanically assisted electrochemical grinding process. Now coming to the zone 3, the material is in this zone 3, the material is totally removed by electrochemical dissolution only. Zone 3 starts at the point where the wheel lifts off the work surface. See, finally, first, when the wheel is rotating like this, first it will touch the top point of this work surface, and then it will come down, and then finally it is going to move in the upward direction. While it is going to move in the upward direction, some of the grinding as abrasives will touch the surface of the workpiece. In this place, the pressure is released slowly, and there also the some of the material is removed purely because of the electrochemical dissolution. This zone contributes to the removal of the scratches, bursts that might have formed in the zone 2. So in the zone 2, the maximum amount of material is removed. So during this machining in the zone 2, whatever the burrs are formed or some scratches are formed because of the sharp edges of the grinding wheel, those burrs or scratches are removed by means of this zone 3. Finally, while the grinding wheel is going up in the downward direction, the extreme edges of this grinding abrasive particles touch, and it removes the a small, very small amount of material from the workpiece, and it removes the scratches and burrs. Now coming to the machining tool, how it exactly work in electrochemical grinding process. The electrochemical grinding systems are very much similar to the conventional grinders. In electrochemical grinding system, the machining area is made up of non-corrosive material, and the power is applied through the spindle, either with help of the brushes or mercury coupling. So this later one, the mercury coupling carry more current than this through the spindle. The probability of short circuiting during the ECG, electrochemical grinding, is very low because of the presence of the protruding abrasives, which creates a positive inter-electrode gap. Hence, in this system, there is a less need of having the short circuit cutoff voltages. Create a positive electrode. Hence, in this system, there is a less need of having a short circuit of cutoff devices. The five different kinds of electrochemical grinding operations can be formed, like electrochemical cylindrical grinding, electrochemical form grinding, electrochemical surface grinding, electrochemical phase grinding, and electrochemical internal grinding. The electrochemical cylindrical grinding is the slowest process because of the limited area of contact between the wheel and workpiece. So in cylindrical grinding process, the process is very slow because of the very less area of contact between the tool and workpiece. However, in electrochemical phase grinding, it is the fastest process because of the maximum area of the contact between the anode, that is the workpiece, and the cathode. So in case of this electrochemical grinding process, the area of contact is slow. Area of contact between the grinding wheel and the workpiece is low. That's why it's a slow process. And in case of the phase grinding, there is a large area of contact between this tool, that is the grinding wheel, and the workpiece. So the maximum amount of material is removed, and that is a fast process. Uneven wheel wear can be controlled by providing a oscillating motion of the workpiece. So because of this one, automatically the wheel wear will be uniform in machining process. In electrochemical surface grinding, the workpiece reciprocates. Means the tool will be the grinding wheel will be constant, and the tool will be reciprocates in the forward and backward direction. In electrochemical internal grinding and electrochemical form grinding are same as conventional internal and form grinding operations. Now coming to the characteristics of this electrochemical grinding process. The performance of this electrochemical grinding process purely depends on various process parameters such as wheel speed, workpiece feed, and electrolyte type, and concentration of electrolyte, and delivery method, current density, and wheel pressure, etc. So if you select appropriate conditions, appropriate process parameters, then it is going to affect like on MRR and surface finish. The current density is one of the most important parameters that influence the process performance. This current density plays a vital role in machining process, in electrochemical machining process. The metal removal rate in electrochemical grinding is also governed by this current density. Means we already discussed this current density plays a vital role in electrochemical grinding process. It will affect on MRR also. With higher current density, automatically what will happen? Both metal removal rate and surface finish will be improved. If the applied voltage is, this is about this current density. Suppose coming to this voltage, if the applied voltage is very high, usually it is range in between 4 to 15 volts. If we supply more than this, automatically what will happen? It may reduces or damages or deteriorates the surface finish of the machined workpiece, as well as damage to the tool. There is a grinding wheel also. So that we have to maintain the voltage in between the 4 to 15 voltage. The presence of such conditions is perceived by spark formation at the front of the wheel. Suppose if your voltage is more than this 15 volts, automatically the spark will be developed, and because of that spark, the damage of the tool or the damage of the workpiece may take place. The selection of an appropriate feed rate to the tool is also important. Means how much, how fastly, or what is the feed rate we are going to give in this electrochemical grinding process is also very much important. If it is higher than the required one, then what will happen? The abrasive particles will prematurely detach from the wheel and leading to the excessive wheel wear. So if the feed rate is more, then automatically these abrasive particles will detach, means it is not going to remove more material, and finally what will happen? The leading to excessive wheel wear will be takes place, means the tool life will be reduced. If it is lower than the required one, what will happen? The larger overcut will be, means it is going to take more amount of time on the surface of the workpiece, and then automatically it removes the more amount of material. Finally, if the metal removal rate is increases, the poor surface finish will come into the picture. The inter-electrode gap is usually a quarter of a millimeter while using a freshly dressed wheel. Suppose if you use a new grinding wheel, then we have to maintain a inter-electrode gap of quarter of a millimeter. In millimeter, 1/4 of the millimeter gap we have to maintain. The surface speed of the wheel is in the range of 1200 to 1800 meters per minute. So this much of surface speed we have to maintain in electrochemical grinding process for better conditions. The metal removal rate is achieved during this electrochemical grinding may be as high as 10 times compared to the conventional grinding on hard materials, which is having hardness above having greater than 65 HRC. But the tolerances obtained in ECG are poorer when comparison to the conventional grinding process. The minimum inside corner radius of 0.25 mm and outside corner radius of 0.025 mm can be produced by this electrochemical grinding process. The surface finish obtained by electrochemical grinding process ranges from 0.1 to 0.8 micrometer. The surface produced by this ECG is free of grinding scratches and burrs. So no burrs or no scratches will be remained on the surface of the component which is machined by this electrochemical grinding process. The surface finish produced on non-homogeneous materials during this electrochemical grinding is better than that produced during this conventional grinding process. And coming to this last point of this characteristics, the electrochemical grinding is a cold process, means the temperature produced during this machining process is less than 100 degrees centigrade. Thus, because of this less temperature produced during this machining process, it prevents the structural damage and grinding cracks. However, electrochemically ground specimen shows relatively poor fatigue strength. So whatever the materials produced by this electrochemical grinding process, those components having the poor fatigue strength, possibly due to stray current attack of the workpiece surface, and which leaves a series of pits that acts as a sites for fatigue crack initiation. Finally, its meaning is, so whatever the components we produced by this electrochemical grinding process are having less fatigue strength. Now coming to the applications, this electrochemical grinding is economical for grinding carbide cutting tool inserts. A microscopic study of this electrochemical ground surface of the cemented carbide do not reveal any damage to the microstructures, micro cracks, or any other defects. And this electrochemical grinding process is also used to reprofile the worn locomotive traction motor gears. So whatever the damage is happened to this traction motor gears which were using in these locomotives, those worn places can be reprofiled by means of this electrochemical grinding process. Usually the wear marks from the gear tooth surface are removed by removing as much as 0.38 mm thick layer of the material. And this process do not have any effect on gear hardness. And ECG, this electrochemical grinding is also used for burr-free sharpening of hypodermic needles, grinding of superalloy turbine blades, and form grinding of fragile materials which are used in aerospace sector.